In April of 2021, in a paper in the Astrophysical Journal Letters, an astronomer at the University of Colorado Boulder named Meredith MacGregor and her collaborators reported something that, at the time, was the most extreme stellar flare ever measured at any wavelength on any of our local star systems. The flare came from Proxima Centauri, the closest star to our Sun, 4.2 light-years away in the constellation Centaurus. At its peak, the flare brightened the star in ultraviolet light by a factor of about 14,000, not by a factor of 2, not by a factor of 10, 14,000 times brighter than the star's normal output. The duration of the flare was about 7 seconds. 7 seconds on a star that had been quietly burning hydrogen at low intensity for billions of years, in which it released in the high-energy bands of the spectrum more radiation than it normally puts out in years of quiet operation. The team observing the event with a coordinated network of 9 instruments across the radio, infrared, visible and ultraviolet bands watched the flare unfold in real time and recorded the data for analysis later. What none of the team explicitly said in the original paper, but which is the unavoidable implication of the result, is that any planet orbiting Proxima Centauri in its habitable zone, including the one we know to exist there, was directly bathed in that flare. And the flare, by the team's own calculations, was capable of doing more atmospheric damage to a habitable zone planet in those 7 seconds than the entire normal output of the star would do over many decades. The planet at the center of this story is called Proxima Centauri b. It was discovered in 2016 in the closest star to our Sun, in an orbit where surface liquid water could in principle exist. It has been, since its discovery, one of the most discussed exoplanets in popular astronomy. The closest, possibly habitable world. The planet that, if anywhere outside the solar system has life, would be the first place we could realistically look. And here is what almost nobody outside exoplanet astronomy has, until quite recently, sat with carefully. The planet may already be dead. If you find that as fascinating as I do, hit subscribe. Pour yourself something warm, get comfortable, and settle in. Because tonight we are going to walk slowly through the strange and quietly mournful story of the closest possibly habitable world we know about, of how we found it, of why we hoped, of what subsequent observations have revealed, and of why the most likely current state of the planet is one in which whatever atmosphere it once had has been stripped away, and whatever life might have existed on its surface in earlier eras has, by now, been gone for a very long time. Now let's ease into it. Part 1. The closest star. Proxima Centauri is, by every measurement we have made of it, the nearest star to our own Sun. The distance is 4.246 light-years, give or take a few thousandths of a light-year, depending on which year of measurement you trust. Light, from Proxima Centauri reaching Earth tonight, left the star a little over 4 years and 3 months ago. Anybody alive in the year 2022, when the photons that arrived tonight started their journey, was alive when this story's most recent chapter began. The star is faint. It has a magnitude of about 11. Which is well below the threshold of unaided eye visibility. To find it, you need a small telescope, a star chart, and a patient evening. Even with a telescope, the star is unimpressive. A small dim red point against the much brighter background of its 2 larger companion stars, Alpha Centauri A and Alpha Centauri B, which together with Proxima form a triple star system. The bright Alpha Centauri pair, visible to the naked eye in the southern hemisphere, has been catalogued and studied since antiquity. Proxima itself, a small, dim red dwarf, gravitationally bound to but orbiting at a great distance from the bright pair, was not even discovered until 1915. There is a small but interesting piece of stellar history worth mentioning here. The Alpha Centauri system, the bright pair visible to the naked eye, has been catalogued since the time of the ancient Greeks. The two bright stars are the nearest sun-like stars to our own. They have been the subject of countless astronomical studies over the past century. Modern parallax measurements give a distance of about 4.37 light-years to the bright pair. By the standards of the local galactic neighborhood, they are very close, but they are not quite the closest. In 1915, careful observations revealed that there was a third star, much fainter, gravitationally bound to the bright pair, but orbiting at a great distance from them. The third star was, by parallax measurements, slightly closer to Earth than the bright pair, by a small amount, but a real one. The third star was given the name Proxima, the Latin word for nearest. The discovery was made by a Scottish astronomer named Robert Innes, working at the Union Observatory in Johannesburg, South Africa. Innes had been carefully comparing photographic plates of the Alpha Centauri region, looking for stars whose proper motion across the sky matched the proper motion of the bright pair. Stars that move together in this kind of survey are generally physically associated, members of a common stellar group or system. Innes found a faint star whose proper motion was very close to that of Alpha Centauri. The star turned out, on parallax measurements, to be slightly closer to Earth than the bright pair. Not by much, but slightly. The star was named Proxima, the Latin word for nearest, because it was, by the new measurements, the nearest of the three stars to our Sun. The closest star to our Sun, as it turned out, was not the bright pair that had been visible since antiquity. It was a small, dim red dwarf, far below the threshold of unaided eye visibility, that nobody had even noticed until the early 20th century. The actual nearest neighbour, in the cosmic sense, had been hiding in plain sight for the entire history of human stargazing. There is something almost touching about the long obscurity of Proxima Centauri. The closest star to our Sun, the nearest neighbour in the local stellar neighbourhood, was a star that nobody had thought worth paying much attention to until quite recently. The brighter pair, Alpha Centauri A and B, had received almost all of the attention. They were the more obvious candidates for hosting interesting planets. The dim red companion orbiting at a great distance was too faint, too small, too red, too apparently boring to be a priority target. That neglect lasted, more or less, for the entire 20th century. The star was catalogued, its parallax was measured, its proper motion was tracked, its overall properties were known, but almost nothing in the way of careful, long-term study was done on it specifically. The community, when it thought about nearby, possibly habitable worlds at all, thought about them in the context of sun-like stars, where the existing biological intuitions made sense. Red dwarfs like Proxima were, at most, a footnote. For most of the 20th century, Proxima Centauri was studied as a curiosity. It was the nearest star, but it was small, dim, and red. It did not, by the standards of the time, look like a likely host for interesting science. Most planet-hunting programs until the late 20th century focused on sun-like stars in the assumption that habitable planets, if they existed, would form around stars similar to our own. Red dwarfs, with their flares and their tidally locked habitable zones, were considered less promising. That picture began to shift in the 2010s as the practical advantages of red dwarf systems for exoplanet detection became clearer. Red dwarfs are the most common kind of star in the galaxy. They make up perhaps 70 or 80% of all stars. The transit signals from Earth-sized planets around them are much larger than the equivalent signals around Sun-like stars. The radial velocity wobbles induced by Earth-mass planets in close orbits are larger too. By every observational metric, red dwarfs are easier targets for finding small planets than Sun-like stars are. The trade-off is the harsher stellar environment, but the trade-off only matters if you can detect the planets in the first place. By the early 2010s, several teams were specifically targeting nearby red dwarfs in dedicated radial velocity programs. One of the most ambitious was the Pale Red Dot program, led by an astronomer named Guillaume Anglada Escudé, then at Queen Mary University of London. The program used the HARPS spectrograph at the European Southern Observatory in Chile to monitor a list of nearby red dwarfs over an extended period, looking for the small periodic Doppler shifts that would indicate planets. Proxima Centauri, as the closest red dwarf to Earth, was one of the highest priority targets. The observations ran through 2015 and into early 2016. By the spring of 2016, the team had accumulated enough data to extract a clear signal. The signal, when it was confirmed by independent reanalysis of older HARPS data, was the wobble of a planet with a mass of at least 1 and a 10th times Earth's in an 11-day orbit, in the part of Proxima Centauri's neighborhood where, given the right atmosphere, surface liquid water could exist. There is a small detail about the Pale Red Dot program that is worth pausing on because it tells you something about how this kind of discovery actually arrives. The program name itself was a reference to Carl Sagan's famous pale blue dot photograph of Earth, taken by Voyager 1 from 6 billion kilometers away in 1990. Sagan's image and the passage he wrote to accompany it had become, in the decades since, one of the most quoted pieces of popular astronomy in the world. The Pale Red Dot program, by choosing that name, was making an explicit statement of intent. They were looking for the next pale dot, the closest, possibly habitable world, the planet that, if it was found, would extend the imagination of where else in the cosmos might be like our home. The program released its data in real time in an unusual public engagement experiment for an exoplanet survey. As the observations came in, the team posted updates online, allowing the public to follow the progress of the search. The approach was, at the time, somewhat unusual for the field. Most exoplanet surveys keep their data private until publication. The Pale Red Dot program made the search itself a kind of shared experience, with the audience watching the data accumulate and the signal slowly emerge from the noise. By March of 2016, the signal was clear enough that the team began preparing the discovery paper. The journal review process, which is normally fast for high-impact results, took several months. By August, the paper was accepted and the team made the announcement. There is a particular emotional weight to the moment when a team confirms that a long-suspected signal is real. The Pale Red Dot program had been monitoring Proxima Centauri intensively for many months. The team had been expecting that if there were a planet in a habitable zone orbit, the radial velocity wobble would be detectable. The signal had been visible in the data for some time, but the team had wanted multiple independent confirmations before publishing. When the confirmations came in sometime in the late winter or early spring of 2016, the team knew, with high confidence, that the closest star to the Sun had a planet in its habitable zone. That kind of moment in the working life of an exoplanet researcher is rare. Most discoveries are smaller. Most candidates require years of follow-up. Proxima Centauri b, by being so close, was confirmed quickly. The team's announcement, when it came in August, was, in some sense, the public version of a fact the team had been quietly sitting with for months. The team announced the discovery in August of 2016 in a paper in Nature. The planet was named Proxima Centauri b by the convention of the field, the little b indicating that it was the first confirmed planet around the star. The announcement was, by exoplanet discovery standards, a major event. The closest star to our Sun, it turned out, had a habitable zone planet. The closest possibly habitable world to Earth was, by every measurement, 4.24 light-years away. Part 2. Why this looked like the moment. The discovery, when it was announced, captured the popular imagination in a way that few exoplanet announcements before or since have. The reason was the proximity. The closest, possibly habitable planet to Earth was, in some sense, the most personally relevant exoplanet ever found. Other systems with potentially habitable worlds were tens or hundreds of light-years away. Proxima Centauri b, at 4.24 light-years, was at a distance that, by every imaginable future technology stretch, might one day be reachable. The Breakthrough Starshot project, announced just a few months earlier, in April of 2016, by the Russian-Israeli billionaire Yuri Milner, had proposed sending tiny laser-driven probes to nearby star systems at 20% of the speed of light. The technology required for such a mission did not yet exist, and would not for at least decades, possibly longer. But the proposal had identified Alpha Centauri specifically as the most promising target system for such probes. The Proxima Centauri b discovery, just months later, gave the Starshot vision a specific destination, not just any nearby star, a nearby star with a habitable zone planet. There is something genuinely emotional about a discovery announcement of this kind, even within the careful community of professional astronomers. The discovery paper, when it was finalized, included acknowledgements to dozens of contributors. The team had been waiting for the right moment to announce. The press conference held at the European Southern Observatory's headquarters in Garching, Germany, was attended by science journalists from around the world. The announcement was carefully worded to convey the significance of the result without overpromising. The subsequent press cycle, despite this careful language, ran with the most dramatic possible interpretation. The press coverage in the late summer of 2016 reflected the excitement. Major newspapers carried the announcement on their front pages. NASA produced commemorative graphics. Popular astronomy publications devoted entire issues to the discovery. The planet, briefly, became one of the most famous exoplanets in the world. Within the science community, the response was more cautious, but still optimistic. The discovery paper itself, by Anglada Escudé and his collaborators, was careful to note the various uncertainties about the planet's properties. The mass, given by radial velocity alone, was a minimum value, not the actual mass. The radius was not measured at all because the planet does not transit its star from our point of view. The composition, given only the minimum mass, was unconstrained. Whether the planet was an Earth-like rocky world, or a Neptune-like ice giant, or a water world, or something else entirely, could not be determined from the radial velocity data alone. The headline finding that the planet was in the habitable zone depended on assumptions about its atmospheric properties that the data could not test. But all of these caveats, in the public framing, were secondary. The headline was that the closest star to the Sun had a habitable zone planet. The headline was correct, in the strict sense. The implications, as far as anyone could tell in 2016, were profound. If the closest star to our Sun had a planet that could in principle support life, then habitable planets around small dim red dwarfs were almost certainly very common. The galaxy was, on this picture, full of potentially habitable worlds. That picture, however, depended on one specific assumption that, by 2017 and 2018, was beginning to come under scrutiny. The assumption was that Proxima Centauri b, despite orbiting an active flaring red dwarf, had retained an atmosphere of the kind necessary for surface liquid water. If the planet had been stripped of its atmosphere, the habitable zone calculation would not apply. The planet's surface, exposed directly to the stellar wind and the high-energy radiation of the host star, would not be habitable in any meaningful sense, regardless of its orbital position. The atmospheric stripping question, which had been a theoretical concern for years, became, in the years after the Proxima Centauri b discovery, the central scientific question about the planet. Part 3. The hostile star. To understand the atmospheric stripping question, you have to understand what kind of star Proxima Centauri actually is. Proxima is an M5.5V red dwarf. The classification puts it firmly in the category of small, cool, dim stars, with a mass of about 12% of the Sun's mass and a luminosity of about a 15,000th of the Sun's. The star is, in absolute terms, very dim. Its total energy output is small, but the star is also, by the standards of stellar physics, unstable. Red dwarfs of this size class, especially the more active ones, exhibit frequent and intense magnetic activity. Magnetic activity, in stellar terms, means flares, coronal mass ejections, enhanced ultraviolet output, enhanced X-ray output, and a strong stellar wind. The instability is intrinsic to the kind of star. M-dwarfs, in their structure, have a deeper convective zone than Sun-like stars. The convection drives the magnetic field, which is the engine that produces flares. Smaller red dwarfs, particularly those near the boundary with brown dwarfs, are fully convective, meaning the entire star is in a state of constant, turbulent overturning all the way down to the core. The fully convective M-dwarfs are, on average, more magnetically active than the partially convective ones. Proxima Centauri, with its mass right around the boundary, is in the active range. The flaring of Proxima Centauri has been observed for as long as we have had instruments capable of measuring it. The first reliable detections of stellar flares from Proxima go back to the 1950s. In the decades since, hundreds of flares have been catalogued. The energies of typical Proxima flares are comparable to large solar flares, perhaps somewhat lower in absolute energy, but much larger relative to the star's quiescent output. The cumulative effect of these flares on a habitable zone planet over geological time has been a topic of study since long before Proxima Centauri b was discovered. There is a piece of stellar physics that is worth pausing on, because it explains why M-dwarf flaring is fundamentally different from solar flaring. On our own Sun, the convective zone, where energy is transported by the bulk movement of hot plasma, occupies the outermost 30% or so of the star by radius. The inner 70% is the radiative zone, where energy is transported by photons gradually working their way outward through the dense stellar plasma. The dividing line between the two zones, called the tachocline, is where most of the Sun's magnetic activity is generated. Small M-dwarfs, including stars like Proxima Centauri, are different. They are fully convective, meaning the entire star, all the way from the surface to the core, is in a state of constant turbulent overturning. There is no radiative zone, there is no tachocline. The magnetic field is generated by a different mechanism, one that operates throughout the bulk of the star rather than at a specific dynamo layer. The result is that fully convective M-dwarfs, despite their small size, can produce magnetic fields that are, in proportion to their luminosity, much stronger than the Sun's. The flares produced by these strong fields are, in absolute terms, sometimes comparable to the largest solar flares, despite the underlying star being only a tenth or so the mass of the Sun. The fractional energy of the flares relative to the star's quiescent output is therefore much higher. A flare of a given absolute energy on a star that is 1,000 times less luminous than the Sun is in proportion 1,000 times more dramatic relative to the star's normal output. The biological and chemical impact of such flares on a planet in the habitable zone is, correspondingly, much more severe than the impact of equivalent flares on Earth. This is, in some sense, the deeper reason red dwarfs are problematic for habitability. The activity is not a side effect of being a young star, the way the Sun's activity in its early phases was. The activity is built into the structure of the star. It does not go away as the star ages, although it does decrease somewhat. It continues throughout the star's main sequence lifetime, at levels that, on a habitable zone planet, drive substantial atmospheric stripping. In 2016, almost immediately after the discovery, several theoretical groups began publishing detailed models of how Proxima Centauri b's atmosphere would respond to the cumulative flaring of its host star. The early modeling by groups including a team led by Cecilia Garafo at Harvard suggested that the stellar wind from Proxima alone, even ignoring the flares, could substantially erode an Earth-like atmosphere over hundreds of millions of years. The Garafo paper, when it was published in 2016, made specific quantitative predictions about the stellar wind environment at the orbital distance of Proxima Centauri b. The team used three-dimensional magneto-hydrodynamic simulations of Proxima's stellar wind to map out the flow of charged particles in the system. The result was that the planet, in its 11-day orbit, would experience stellar wind pressures hundreds of times stronger than the wind pressure Earth experiences from the Sun. The cumulative effect on a planet without a strong magnetic field would be substantial atmospheric stripping over geological time. The team's quantitative estimates, while uncertain, all pointed in the same direction. The planet would have lost most of its initial atmosphere on the basis of stellar wind effects alone, even before considering the additional effects of flares. A subsequent paper by Tilley and collaborators in 2019 extended the modelling to include the cumulative effect of repeated flaring events. The Tilley analysis, published in Astrobiology, computed the chemistry of an Earth-like atmosphere subjected to thousands of flare events of various magnitudes over geological time. The result, broadly, confirmed the picture from the Garafo work. The atmosphere on the most plausible models would be substantially altered by the cumulative bombardment, with the lighter species selectively lost, the heavier species concentrated in the residual atmosphere, and the surface eventually exposed to direct radiation, as the atmosphere thinned past a critical threshold. These modelling papers, taken together, established the picture that has dominated the field's view of Proxima Centauri b's habitability since the late 20-teens. The picture, in short, is that the planet's atmospheric history has been shaped, over billions of years by the activity of its host star in ways that are very probably incompatible with the kind of habitability we would imagine when we think about Earth-like worlds. With the flares included, the time scale for total atmospheric loss was potentially shorter still. The modelling depended on assumptions that were, in 2016, poorly constrained. The planet's magnetic field strength, which would partially shield it from the stellar wind, was unknown. The planet's atmospheric composition, which would determine its susceptibility to stripping by different wavelengths of radiation, was unknown. The history of the host star's activity, particularly during the early stages of the system's life when M-dwarfs are typically more active than they are today, was poorly understood. The conclusions of the early models were, therefore, broad in their range. Some scenarios suggested the planet could retain an atmosphere for billions of years. Others suggested it would lose any Earth-like atmosphere within 100 million years. The observational tests of these models were, in 2016, not yet possible. The planet does not transit its star from our point of view, so atmospheric transmission spectroscopy is unavailable. Direct imaging, separating the planet's light from its stars, was beyond the capability of any instrument then in operation. Radial velocity, which had detected the planet, could not say anything about its atmosphere. The question of whether the planet had an atmosphere at all in 2016 was open. It would remain open for years while observations of the host star's activity gradually accumulated. Part 4. The Howard Flare and the Early Warning. In March of 2017, a team led by Ward Howard at the University of North Carolina at Chapel Hill detected an extreme flare from Proxima Centauri using the Evriscope, a small wide-field telescope array in Chile. The flare, which lasted about 2 minutes, brightened the star by a factor of about 68 times in visible light at its peak. By the standards of stellar flaring, that was a major event. By the standards of what astronomers had previously assumed about Proxima's behavior, it was a wake-up call. The Howard flare, as it came to be known, was not the largest flare ever detected from any star. Larger flares had been seen on more active M-dwarfs in the years before. But the flare was the largest ever directly observed from Proxima specifically, and it was important because it demonstrated that Proxima, despite its relatively low overall activity level by red dwarf standards, was capable of producing extreme events that, on the timescales relevant for atmospheric stripping, mattered. The Howard team's observation was, in some sense, fortunate. The Evriscope had been operating for a relatively short period when the flare occurred. The team had been planning to monitor the southern sky generally, looking for transient events of various kinds. Catching a major flare from Proxima Centauri specifically was not the central goal of the campaign. But because the instrument was operational and pointed at the right part of the sky at the right time, the flare was caught with high time resolution and across multiple filters. The data, when reduced, gave a much clearer picture of the flare's structure than had been possible from any previous Proxima flare observations. The team's analysis of the flare, published in the Astrophysical Journal Letters in 2018, included a calculation of how often such events occur. The calculation, based on the statistical distribution of flares observed during the campaign, suggested that flares of this magnitude, or larger, occur on Proxima roughly 5 times per year. That is, by any reasonable standard, frequently. 5 extreme events per year for billions of years adds up to something genuinely large in cumulative terms. The implications for Proxima Centauri b's atmosphere, when the team did the calculation, were grim. The energy delivered to the planet in the form of high-energy ultraviolet and X-ray radiation by a single Howard-scale flare was estimated to be roughly equivalent to several years' worth of normal stellar output. 5 such flares per year, sustained over the lifetime of the system, would deposit on the planet's atmosphere an enormous cumulative dose of damaging radiation. The atmospheric photochemistry on this picture would be substantially different from what it would be in a quieter stellar environment. There is a small piece of context worth adding about the Everyscope itself, because it tells you something about the kind of equipment that produces results like this. The Everyscope is, by the standards of professional astronomy, a small system. It consists of an array of small, commercial-grade cameras mounted on a single tracking mount, all observing the entire visible sky at once with a very wide field of view. The total cost of the Everyscope, when it was built, was a few $100,000. By the standards of major space telescopes, that is a tiny budget. By the standards of what professional observatories typically spend on instrumentation, it is modest. But the Everyscope was perfectly suited to catching extreme stellar flares, because the flares are short-duration events that require continuous monitoring of many stars at once. A traditional astronomical observation which targets one or a few stars at a time and switches between them is unlikely to catch a flare unless the observer happens to be looking at the right star at the right moment. The Everyscope, by observing the entire sky continuously, catches every flare from every visible star all the time. The Howard flare on Proxima was, in some sense, an inevitable detection given the operational mode of the instrument. The Howard flare on its own was not enough to settle the atmospheric question. The flare was a single event, and the calculation of cumulative effects depended on assumptions about flare frequency and energy distribution that were, even in 2018, uncertain. But the result raised the level of concern. The picture of Proxima Centauri b as a quiet, habitable zone world, retaining an Earth-like atmosphere over billions of years, became much harder to maintain after the Howard flare was published. Part 5. Here is where the picture really wobbles. Here is where the picture really shifts. In April of 2019, a coordinated multi-wavelength observing campaign caught Proxima Centauri in the middle of an event that, when it was finally analysed and published in 2021, would turn out to be the most extreme stellar flare ever measured at the wavelengths it covered. The campaign was led by Meredith MacGregor at the University of Colorado Boulder in collaboration with researchers at NASA, the University of Sydney, and several other institutions. The team had 9 instruments observing the star simultaneously, covering a wavelength range from radio through ultraviolet, hoping to catch a flare and characterize its full spectral structure for the first time. What they caught on the 1st of May 2019 exceeded their expectations. The flare, when the data was reduced, showed a peak ultraviolet brightening by a factor of about 14,000, sustained for about 7 seconds before declining. The peak X-ray brightening was about 1,000 times. The radio emission, which carries information about the energetic particles produced in the flare, was also extreme. Across the full wavelength range, the event was the most energetic flare ever measured from Proxima specifically, and one of the most energetic flares ever measured from any nearby red dwarf. The team's coordinated observing campaign was, by the standards of M-dwarf flare research, ambitious. Catching a flare that crosses the full electromagnetic spectrum requires that all of the instruments be operating simultaneously in their respective wavelength bands with high time resolution. Coordinating 9 instruments across 4 continents, all to be ready to observe a single star for an extended period with the goal of catching a transient event that might or might not happen, is a logistical challenge. The team had been planning the campaign for months. The observations themselves ran for several weeks. The flare, when it finally happened on the 1st of May 2019, was a single 7-second event against a backdrop of weeks of mostly quiet observation. The team published the result in the Astrophysical Journal Letters in April of 2021, more than 2 years after the actual observation. The delay between observation and publication is normal for this kind of detailed, multi-wavelength analysis, where the data has to be calibrated, modelled, and cross-checked across many different instruments before any conclusions can be drawn. When the implications of the flare for Proxima Centauri b were calculated, the picture was unambiguous. The high-energy radiation delivered to the planet during those 7 seconds integrated across the spectrum was capable of doing significant atmospheric damage to a habitable zone world. If the planet had any of the kinds of atmospheres that would be needed to support surface liquid water, this single event could have stripped a substantial fraction of it. Multiple such events over the planet's history could have stripped most or all of any plausible original atmosphere. There is a small piece of context worth adding about the flare's energy budget. The total energy released in the flare, integrated across all wavelengths, was estimated at about 10 to the 32nd joules. By the standards of solar flares, that is a very large event. It is comparable to the very largest solar flares ever recorded. By the standards of the star's normal output, it was a much larger fractional event. Proxima's quiescent luminosity, integrated over the 7-second duration of the flare, would have been about 10 to the 24th joules. The flare in 7 seconds released roughly 100 million times the star's normal energy output for that duration. That kind of fractional event integrated over the lifetime of the star has cumulative effects that are very different from what the Sun's flares produce on Earth. The MacGregor flare, more than the Howard flare, 2 years earlier, was the result that changed the conversation about Proxima Centauri b. After 2021, the working assumption in the field shifted. The planet, which had been described in the years immediately after its discovery as our nearest possibly habitable world, was increasingly being described in the careful language of researchers as a planet whose habitability was, in the strict sense, doubtful. Not impossible. Not ruled out, but genuinely doubtful in a way that the early popular framing had not captured. Let me sit with that for a moment. The closest possibly habitable planet to Earth on the most current models has probably had any Earth-like atmosphere stripped away by the flaring of its host star. The planet is still there. It is still in the habitable zone by the temperature definition. But the conditions on its surface after billions of years of stellar bombardment are most likely not what we would call habitable. Part 6. What flares actually do to atmospheres. To understand why the MacGregor flare was so significant, you have to understand in some detail what high-energy stellar radiation actually does to a planet's atmosphere. The first effect is thermal. High-energy ultraviolet and X-ray photons, when they hit a planet's upper atmosphere, deposit their energy through ionization. The ionized gas, which is much hotter than the neutral gas, expands. The expansion drives an upward flow of gas called a hydrodynamic outflow that lifts material from the upper atmosphere into space. Some of the lifted gas falls back. Some of it escapes the planet's gravity entirely. The cumulative effect, over time, is a slow loss of atmosphere to space, with the rate depending on how much energy is being deposited and how strong the planet's gravity is. The second effect is photochemical. High-energy ultraviolet radiation, especially in the wavelength range below 200 nanometers, breaks apart molecules in the upper atmosphere. Water vapor, when broken apart, produces hydrogen and oxygen. Hydrogen, being light, tends to escape to space more easily than oxygen, so a water-rich atmosphere, when subjected to extreme ultraviolet radiation, tends to lose its hydrogen disproportionately, leaving an oxygen-enriched residue. Over geological time, this kind of selective loss can substantially alter the chemistry of an atmosphere, even if the bulk mass loss is moderate. There is a comparison with Earth's own atmospheric history that helps put this in perspective. Earth, when it formed about 4.5 billion years ago, had an atmosphere that was very different from the one we breathe today. The early atmosphere was dominated by hydrogen, helium, water vapor, methane, and ammonia, in proportions roughly similar to the bulk composition of the protoplanetary disk. Within a few 100 million years, most of the lightest gases, the hydrogen and helium, had escaped to space. The remaining atmosphere was mostly water vapor and carbon dioxide, with smaller amounts of nitrogen and trace gases. Over the following billions of years, Earth's atmosphere continued to evolve. The carbon dioxide was gradually drawn down by the weathering of silicate rocks. Water vapor rained out into the oceans. Nitrogen, being relatively unreactive, accumulated. Oxygen, after the rise of photosynthetic life, eventually came to dominate the atmosphere alongside nitrogen, producing the breathable mixture we have today. The whole evolution took place against a backdrop of a relatively stable sun, with comparatively mild flaring activity. The atmosphere, despite some early loss, was not heavily stripped over geological time. On Proxima Centauri b, the picture is, by every model, very different. The planet's atmosphere has been subjected to flaring activity many times more intense than what Earth experienced. Whatever the original atmospheric composition was, the cumulative loss to space, over billions of years, would have been substantial. The planet may currently have a much thinner atmosphere than Earth's, or possibly none at all, regardless of what it started with. The third effect is via the stellar wind. The wind from an M-dwarf is, in absolute terms, much stronger than the wind from a sun-like star. Especially during flare events, the coronal mass ejections that accompany the flares can deliver enormous amounts of charged particles directly to a planet's atmosphere. If the planet has a strong magnetic field like Earth's, most of the charged particles are deflected. If the planet has a weak magnetic field or no magnetic field, the charged particles interact directly with the upper atmosphere, doing chemistry and stripping mass. The cumulative effect, again, depends on the planet's magnetic field strength, which for Proxima Centauri b is unknown. The fourth effect is on the surface, if any radiation reaches the surface. On Earth, the atmosphere absorbs almost all of the ultraviolet radiation, particularly the most damaging short-wavelength ultraviolet, before it reaches the ground. Without an atmosphere, or with a thin atmosphere, the surface is directly exposed. Any complex organic molecules at the surface are broken apart. Any biological organisms that evolved under more shielded conditions are damaged or destroyed. Surface chemistry on a planet without atmospheric protection is dominated by photolysis rather than by the kinds of slow chemistry that life depends on. The combined effect of these processes, integrated over billions of years, is what the atmospheric stripping models are trying to calculate. The calculation depends on many parameters that are not directly measurable. the planet's initial atmospheric inventory, its magnetic field strength, the history of the host star's activity, particularly in the early phases of the system's life, the evolution of the stellar wind over time, the detailed chemistry of the atmosphere as it loses mass. There is one further mechanism worth mentioning which has been studied in detail in the modelling literature, called atmospheric ion escape. Charged particles from the stellar wind, when they interact with the planet's atmosphere, can transfer momentum to atmospheric ions, accelerating them beyond the planet's escape velocity. The mechanism is particularly effective for an unmagnetized or weakly magnetized planet, where the stellar wind has direct access to the upper atmosphere. Once the upper atmosphere is being depleted by ion escape, the rate of loss can be very large, particularly during flare events when the stellar wind is enhanced by orders of magnitude. The cumulative effect over billions of years is, by every model, substantial. The planet may have lost most of its initial atmosphere through this process alone, even before factoring in the photochemical and thermal effects. For Proxima Centauri b specifically, the best current models, as of the time of this telling, suggest that an Earth-like atmosphere, started with an Earth-like initial inventory, would be substantially depleted within hundreds of millions to a few billion years. Whatever atmosphere the planet currently has, if it has any at all, is unlikely to be similar to Earth's. The most likely scenarios are a very thin atmosphere, dominated by heavy gases that are harder to strip, with relative levels of various chemical species that reflect billions of years of differential loss. I am not saying that the planet has no atmosphere. I am not saying it cannot harbour life of any kind anywhere. I am not saying that the question is closed. What I am saying is something quieter than any of those. What I am saying is that the conditions that would be needed for the planet to currently host an Earth-like surface environment, with surface liquid water, with a thick protective atmosphere, are conditions that, by every model we have, are difficult to maintain in the face of billions of years of Proxima's flaring. The most likely current state of the planet, by the best evidence available, is not Earth-like. Part 7. What might have been. Here is where the story takes its quietest turn. Because the picture of Proxima Centauri b as a planet that is currently inhospitable does not necessarily mean the planet was always inhospitable. It is possible on some scenarios that the planet was once habitable, perhaps with surface oceans, perhaps with a substantial atmosphere, perhaps even with the conditions for life to begin. And that, over billions of years of stellar bombardment, those conditions were lost. The scenario, when you spell it out, has a particular quiet sadness to it. Imagine a planet 4.24 light-years from Earth, in a tight, close-in orbit around a small, dim red star. Imagine the planet, billions of years ago, having an atmosphere thick enough for surface liquid water, having oceans, having continents, having a chemistry similar enough to Earth's that, given the right conditions, the same kinds of prebiotic chemistry that led to life on Earth could have proceeded there as well. There is a particular time scale issue worth noting in this scenario, which is that the early phase of an M-dwarf's life is much more active than the later phases. In its first billion years or so, a star like Proxima Centauri produces flares many times more frequently, and with much higher peak energies than it does in its current middle age. Any planet that formed around such a star and was in the habitable zone would, during the first billion years, have been subject to the most intense atmospheric stripping conditions of its entire history. The early phase, in some sense, is when most of the damage gets done. Whatever atmosphere a habitable zone planet retained after the first billion years would be the atmosphere it largely had to work with for the rest of its history. The timescale of life on Earth is informative here. The earliest unambiguous evidence of life on Earth dates to about 3.5 billion years ago, when the planet was about 1 billion years old. Life took, by the most generous interpretation, several 100 million years to begin once Earth had cooled enough to have liquid water. By that time scale, on Proxima Centauri b, the early high flaring phase of the host star would have already been underway. Whatever atmosphere the planet started with would, by the time conditions might have been right for life, already be substantially eroded. Life on this scenario would have to have begun in conditions that were, by Earth standards, marginal from the start. Imagine on this scenario that life did begin. Simple chemistry first, self-replicating molecules, the earliest forms of metabolism, cell membranes, single-celled organisms, the slow accumulation of biological complexity that, on Earth, took 2 billion years to lead from the first cells to the first complex multicellular life. Imagine this whole process unfolding on this distant world in parallel with what was happening on Earth. Imagine, then, the host star aging. As red dwarfs age, their flaring activity changes. The early phase of an M dwarf's life, in the first billion years or so, is typically the most active. The rate of flaring is high, the intensity of individual flares is high. The cumulative atmospheric stripping is at its strongest. Various studies have estimated that an M dwarf in its first 100 million years can be perhaps 10 or 20 times more active than the same star will be when it has reached its current middle age. The flaring rates during this early period are not just somewhat higher than they are now, they are dramatically higher. A planet that formed in the habitable zone of an M dwarf would, during the first 100 million years, experience a more intense radiation environment than anything we have direct experience of. As the star ages, the activity gradually declines, but never to zero. The flaring continues at a lower rate throughout the star's main sequence lifetime. Imagine on this scenario that the planet's atmosphere was being stripped throughout this process. Slowly, over hundreds of millions of years, the atmosphere thinned. The oceans, no longer protected by a thick atmosphere, began to evaporate and be photochemically dissociated by the high-energy radiation from the star. The hydrogen escaped to space. The oxygen freed from water molecules accumulated in the upper atmosphere, where it was further attacked by stellar wind and flares. The chemistry shifted. The conditions on the surface increasingly became different from what they had been. Imagine on this scenario that life on the planet went through the same kind of long, slow, evolutionary path that life on Earth has gone through. Single-celled organisms, then prokaryotes, then eukaryotes, then multicellular forms. Imagine that these organisms, on this distant world under its dim red sun, did the work of biological complexity, just as Earth life has done, just at a different pace and under different conditions. Imagine that, at some point in this hypothetical evolutionary history, the conditions on the planet started to deteriorate. The atmosphere thinned. The oceans began to be stripped. The radiation environment became harsher. Imagine, on this scenario, the slow process of habitat loss, not catastrophic, not dramatic, just slow, over millions of years. The shorelines of the oceans gradually receded as the water evaporated and was lost to space. The atmospheric pressure gradually fell as gases were stripped. The chemistry of what remained gradually shifted as different gases were lost at different rates. The conditions on the surface slowly became more like Mars and less like Earth. The organisms that depended on the original conditions slowly went extinct. The ones that could survive in the marginal conditions persisted longer, but the marginal conditions themselves continued to deteriorate. Imagine, finally, that any life that had evolved on the planet ran out of habitable conditions. The oceans were gone. The atmosphere was thin, the surface was exposed to direct stellar radiation. Whatever organisms had thrived in earlier eras either died out, went extinct, or retreated into whatever marginal habitats remained, perhaps deep underground, perhaps in the small volume of remaining atmosphere near the terminator, perhaps in some other refuge that we cannot yet imagine. Eventually, perhaps over hundreds of millions of years, the marginal habitats themselves were lost. The last cells died. The chemistry of the surface returned to abiotic. The planet became, by the standards of biology, dead. This scenario is, of course, speculative. We do not know whether Proxima Centauri b was ever habitable. We do not know whether life ever began there. We do not know what the planet's atmospheric history actually looks like. The picture I have just painted is one of several possible histories, and not the most likely one. The most likely history on the current models is that the planet may never have had a thick enough atmosphere to be properly habitable in the first place. Life in this picture never began. But the possibility that the planet was once habitable and then lost that condition is not zero. The proximity of the planet to its star, the timing of the early M-dwarf high-activity phase, the parameters of the original atmosphere, all matter for which scenario is closer to the truth. Different combinations of these parameters give different answers. Some answers leave the planet always uninhabitable. Some leave it habitable now, some put it through a habitable phase and into a current dead state. The space of possibilities, in some sense, includes a quietly mournful possibility that we cannot, on the current evidence, rule out. Let me sit with that. 4.24 light-years from where you are listening around the closest star to our Sun, there is a planet that may be currently dead, may have been alive for some part of its history, may have lost everything it once had to billions of years of stellar bombardment. The story on this telling is not a story of a planet that was never habitable. It is a story of a planet that, perhaps, was once a place and is no longer. Part 8. The atmospheric tests we have not yet been able to do. To distinguish between the various scenarios for Proxima Centauri b's current state, we need direct atmospheric measurements that have, until very recently, not been possible. The planet does not transit its star from our point of view, so transmission spectroscopy, the technique that has given us atmospheric chemistry for many other exoplanets, is unavailable. We cannot, at the time of this telling, measure the chemistry of Proxima Centauri b's atmosphere, if it has one, by the standard methods of the field. What we can in principle do is direct imaging. Direct imaging means separating the planet's light from the stars by some combination of high-contrast optics and adaptive image processing, and measuring the planet's emission spectrum independently. The technique is much more demanding than transmission spectroscopy because it requires the planet's light to be detected in the immediate glare of its host star. For a planet at the orbital distance of Proxima Centauri b, only a few hundredths of an astronomical unit from the star, this kind of imaging is at the very edge of what current instruments can do. There is a useful comparison with the techniques we have used on other planets that helps put this in context. K2-18b, the planet we have spent an evening with previously, transits its star, which is what allowed JWST to do transmission spectroscopy and to detect the methane and carbon dioxide, that made the planet famous. WASPA 12b transits, which is what allowed the orbital decay measurement and the atmospheric mass loss observation, HD 189733b transits, which is what allowed the cobalt blue color determination and the wind speed measurement. Almost all of the most detailed atmospheric characterization of exoplanets in the past 2 decades has been done on planets that transit their stars from our point of view. Proxima Centauri b does not transit. The geometry of its orbit relative to our line of sight simply does not produce transits visible from Earth. This is statistically normal. Most exoplanets do not transit. We only see transits from planets whose orbital planes happen to be edge-on to our viewing direction. The planets we know the most about are the ones that, by accident of geometry, line up the right way. Proxima Centauri b, like most exoplanets, does not. Several teams have been working on direct imaging of Proxima Centauri b for years. The European Southern Observatory's SPHERE instrument on the Very Large Telescope in Chile has attempted direct imaging campaigns. The James Webb Space Telescope, with its coronagraph instruments, has tried as well. As of the time of this telling, no team has yet reported a definitive direct imaging detection of Proxima Centauri b, but the upper limits on the planet's brightness have been steadily improving. There is a small technical point worth adding about why direct imaging of Proxima b is so difficult. The contrast ratio between the planet and the host star in the visible part of the spectrum is roughly 1 part in a billion. The planet is a billion times fainter than the star. To detect the planet, you have to be able to suppress the star's light by at least 9 orders of magnitude in the immediate vicinity of where the planet's image would form. That kind of contrast suppression is, by the standards of any optical system, extreme. The technologies that can achieve it, including coronagraphs and star shades, are at the very edge of what current engineering can produce. The closest thing to direct imaging that has been done on Proxima b specifically has been with the SPHERE instrument on the Very Large Telescope, which has produced upper limits on the planet's brightness, but has not yet definitively detected the planet itself. The next-generation ground-based telescopes, particularly the European Extremely Large Telescope, with its 39-meter primary mirror, will be able to do direct imaging of Proxima Centauri b at high enough signal-to-noise to extract atmospheric information. The ELT is expected to see first light in 2028 or 2029. Within a few years of its first light, the telescope should be producing the first direct atmospheric spectra of Proxima Centauri b. By the early 2030s, we should know definitively whether the planet has an atmosphere, what kind of atmosphere it has, and whether the atmospheric chemistry is consistent with any of the various habitability scenarios. There is a small note worth adding about a related discovery from 2024, which is that the Proxima Centauri system has been shown to host at least 1 and possibly 2 additional planets beyond Proxima b. A second planet called Proxima Centauri d was confirmed in 2022. It is a sub-Earth mass world in a much tighter orbit than Proxima b, with an orbital period of about 5 days. There has also been long-debated evidence for a third planet, Proxima Centauri c, in a much wider orbit at about 5 years, although the detection of ANG-C has been more contested. The system, then, is not a single-planet system. It is a multi-planet system, with at least 2 confirmed planets, and possibly a third. The bombardment by the host star's flares affects all of them, although the consequences for habitability are most directly relevant for Proxima b, which is in the habitable zone. Until then, the question is open. But the direction of the evidence from the flaring measurements and the atmospheric stripping models points strongly toward a planet that has been genuinely affected by its host star in ways that probably make current habitability difficult or impossible. Part 9. Why the proximity matters. Here is a thought that is worth sitting with about why Proxima Centauri b's story matters, even if the planet itself turns out to be uninhabitable. The fact that the closest star to our Sun has a habitable zone planet, even if that planet is currently uninhabitable, tells us something important about how common such planets are. If the closest star to us has one, then habitable zone planets are, almost certainly, very common around small red dwarfs. Most stars on this picture have at least one. Combined with the fact that small red dwarfs make up most of the stars in the galaxy, this implies that the galaxy contains, by every reasonable estimate, billions of habitable zone planets, maybe tens of billions. The rocky planet in the habitable zone on the most recent statistics is one of the most common kinds of object in the universe. But the question of whether those planets are actually habitable in the deeper sense is much harder. Habitable zone position is necessary but not sufficient. The planet also needs an atmosphere that is thick enough, with the right composition, and stable enough over geological time for surface liquid water and biological chemistry to actually be possible. Whether most habitable zone planets meet these stricter conditions is, by every available measurement, much more uncertain. There is a small but meaningful intermediate position worth noting, which is that even if the planet's surface is currently uninhabitable, there could in principle be subsurface habitats where conditions are more favorable. On Earth, we have known since the late 20th century that life exists deep underground in the rocks and pore waters of the lithosphere in conditions that are genuinely extreme. The deep biosphere on Earth contains a substantial fraction of the planet's total biomass. If similar habitats exist on Proxima Centauri b, beneath whatever weathered surface remains, then life of some form might be possible there, even if the surface is, by every meaningful measure, dead. The detection of such subsurface life from many light years away would be essentially impossible with any current technology. The possibility, however, is part of the more nuanced, honest accounting. Proxima Centauri b is a test case. If we can determine definitively what the current state of this specific nearby world is, the result will tell us about the larger statistical question. If Proxima b is currently habitable, despite the flaring of its host star, that suggests that the atmospheric stripping models have been too pessimistic, and that habitable zone planets around active red dwarfs can survive the bombardment. If Proxima b is currently dead, despite once being habitable, that suggests the atmospheric stripping is real and that even nearby, possibly habitable planets do not survive over geological time. Either result, applied to the broader population of habitable zone planets around red dwarfs, has profound implications for how common life-supporting worlds actually are. The proximity of Proxima b makes it the ideal test case for these questions. It is closer than any other comparable system. It is more observable than any other comparable system. The atmospheric measurements we will be able to do on it in the next decade will be more detailed than the equivalent measurements on more distant systems. The answer, when it comes, will be definitive in a way that the answers for more distant systems will not be. That is why the planet, even if it turns out to be dead, is worth studying. Part 10. The honest accounting. I am not saying that Proxima Centauri b is dead. I am not saying that it never had life. I am not saying that current observations rule out all forms of habitability. What I am saying is something quieter than any of those. What I am saying is that the evidence we currently have, from stellar flaring measurements and atmospheric stripping models, points toward a planet that has had its atmosphere substantially eroded over billions of years, and whose current surface conditions are, most probably, not consistent with the kind of habitability we would imagine when we think about Earth-like worlds. The honest position in 2025 is that Proxima Centauri b is a planet whose habitability has gone from probably yes in 2016, when the discovery was announced, to probably not, but not yet definitively ruled out by the time of this telling. The shift has been gradual. It has been driven by accumulated evidence about the host star. It has been argued out in the technical literature in the kind of slow, patient back and forth that does not produce headlines. The popular framing in many places has not entirely caught up. You can still find articles describing Proxima b as the closest, possibly habitable world, with a confidence that the science has not justified for at least several years. That mismatch between popular framing and scientific consensus is, in many ways, characteristic of exoplanet astronomy. The discoveries get framed dramatically when they are first announced. The subsequent careful work, which often reveals complications, gets less coverage. The story, in the popular telling, lags behind the story in the literature. Proxima Centauri b is, in this respect, a typical case. The diamond planet was a typical case. The early days of the K2-18b biosignature claim were a typical case. The pattern recurs because the incentives of the popular science press are different from the incentives of the scientific community. Both pursuits are valuable. They produce different kinds of stories. What we can say with some confidence is that Proxima Centauri b will, over the next decade or so, become much better characterized than it currently is. The extremely large telescope will start direct imaging in the late 2020s. JWST is already attempting coronagraphic imaging. Future missions, including possible ground-based interferometric efforts and the Habitable Worlds Observatory, will provide additional constraints. By the early 2030s, the question of what Proxima Centauri b currently is should be largely settled. The scenario in which it is currently dead, the scenario in which it is currently inhabited, the scenario in which it is somewhere in between, will be distinguished by data, not by speculation. Until then, we wait. We accumulate more flaring measurements. We refine the atmospheric stripping models. We build the next generation of instruments. The planet itself, regardless of what we think about it, continues its 11-day orbit around its small, dim red star, in whatever current state it is in, while the work of finding out is being done by people who will probably not be alive when the answer is finally in. Part 11. The stakes for the broader picture. There is one more sub-question worth pausing on before we leave the technical part of the story. What kind of atmosphere, specifically, would Proxima Centauri b need to currently have to be considered habitable? The answer, by the climate models that have been done for similar planets, is that it would need to be substantial, not necessarily Earth-thick, but thick enough to provide pressure for surface liquid water, thick enough to redistribute heat from the day side to the night side, thick enough to absorb most of the high-energy radiation from the host star before it reaches the surface, thick enough to maintain stable conditions for biological chemistry over geological time. The minimum atmosphere required is, by the most generous models, perhaps a few hundred millibars. The atmosphere actually present, if any, is unknown, but, by the stripping models, may be much thinner than this minimum. The atmospheric inventory required to actually be habitable is also chemistry dependent. An atmosphere of mostly nitrogen and oxygen like Earth's would behave one way. An atmosphere of mostly carbon dioxide, like Venus's, would behave another way. An atmosphere of mostly hydrogen, like the gas giants, would behave still another. The composition that has the best chance of supporting habitability on a tidally locked planet around a flaring red dwarf is debated in the literature. Different models give different optimal compositions. None of them, when applied to Proxima Centauri b, specifically gives a clean prediction. Whatever turns out to be true about Proxima Centauri b specifically, the implications for the broader question of habitable worlds in the galaxy are real. There is a further wrinkle to the broader question that is worth sitting with. Most stars in the galaxy are not sun-like. They are M-dwarfs, like Proxima. If habitability around M-dwarfs is generally hostile because of the flaring problem, then most of the habitable zone planets in the galaxy are not actually habitable. The galaxy on this picture has billions of habitable zone planets, but only a small fraction of them are around stars quiet enough to allow stable atmospheres. The actual number of habitable worlds by this argument would be much smaller than the simple counting suggests. Conversely, if M-dwarf habitability does work, despite the flaring, then the broad picture is much more optimistic. Habitable worlds on this picture are not just common in the abstract sense of being in the right orbital position. They are actually common in the deeper sense of being able to maintain the conditions for life over geological time. The galaxy, on this version of the picture, is genuinely full of habitable worlds around the kind of star that most stars actually are. The question, in short, hinges on which of these pictures is correct, and the question in turn hinges on detailed atmospheric measurements of specific planets like Proxima b. The science is, in this respect, not just about one planet. It is about the bulk character of the galactic habitability landscape. If Proxima b is currently uninhabitable, despite being in the orbital habitable zone of its host star, then the simple counting argument that habitable zone planets are abundant becomes more nuanced. There are many habitable zone planets in the galaxy, but habitable zone is a much weaker condition than actually habitable. The stricter condition of having an atmosphere that survives the host star's activity over geological time may be much more restrictive. The fraction of habitable zone planets that are actually habitable on this picture may be small. If Proxima b is currently habitable against the expectations of the atmospheric stripping models, then the picture is reversed. Habitable zone planets around active red dwarfs do retain atmospheres. The galaxy is, on this picture, full not just of habitable zone planets, but of actually habitable planets. Life, if life arises whenever conditions allow, would be much more common than the pessimistic models suggest. The intermediate scenarios, in which Proxima b has a thin atmosphere, but not a thick one, or has habitable conditions only in some narrow latitude band, or has marginal conditions that are not obvious to characterize, are also informative. They tell us where the boundary lies between habitable and uninhabitable. They tell us what the conditions are that, on a planet like this, lead to which outcome. The galaxy, on these intermediate pictures, has a more nuanced distribution of habitable conditions than the simple yes or no framings suggest. Either way, the answer to the Proxima b question when it comes will reshape our picture of how common life-supporting worlds are. The question is not just about one planet. It is about the kind of planet around the kind of star that is most common in our galaxy. The answer, when we have it, will be applicable far beyond the system that produced it. Part 12. The view from 4.24 light-years. The proximity of Proxima Centauri to our Sun makes the system unique, in a practical sense. Among all known exoplanet systems, 4.24 light-years is, in cosmic terms, very close. The light reaching Earth tonight from Proxima left the star in early 2022. Anybody alive in early 2022 was alive when the photons that arrived tonight started their journey. That short timescale matters because it means that in some hypothetical future technology scenario, the system is in reach. There is a small experiment worth mentioning here which has actually been carried out. In 2008, a private project called Cosmic Call had transmitted radio messages towards several nearby stars, including stars in the general direction of Alpha Centauri. The messages, when they were sent, were intended to be the first deliberate attempts to communicate with any possible civilizations around those stars. The transmission by a single radio dish at a Ukrainian observatory was, in absolute terms, modest. Whether it would even be detectable from a distant planet, given the small dish size and the limited transmission power, is doubtful. But the symbolic gesture was real. We have, as a species, attempted in some small way to send a deliberate signal to nearby stars. The signal, if it makes it to Proxima Centauri at all, will arrive in 2012 plus 4.24 years, which is just past 2016. The transmission was, in some sense, a few decades early for any actual conversation. Even if there were anybody on Proxima Centauri b to hear it, by the time they received it and replied, 8 more years would have passed. The whole exchange, if it is happening at all, is on a time scale that is, in absolute terms, slow, but not impossibly so. A radio message sent from Earth to Proxima would take just over 4 years to arrive. A reply in the absence of any obstacle would take another 4 years to come back. The round trip is under 9 years, well within a single human career. Not long enough to discourage the idea of communication if there were anything on Proxima Centauri b to communicate with. The Breakthrough Starshot project, which we have mentioned in earlier evenings, has identified Proxima Centauri specifically as the most promising target for nearby star probe missions. At 20% of the speed of light, which is well beyond what current technology can achieve, but is the design goal of the Starshot program, a probe to Proxima would take just over 20 years to arrive, plus another 4 years for the data to come back. The total mission duration from launch to first data return is under 30 years. That is, by the standards of any deep space exploration we have ever attempted, very fast. Whether Starshot is ever actually built is, again, an open question. The technology required is well beyond what has been demonstrated, but the proximity of Proxima makes the proposal at least conceivable, which is more than can be said for any other potentially habitable system in the galaxy. If we were ever going to send probes to characterize an exoplanet up close, Proxima Centauri b would be the planet to send them to. There is, however, an entirely different kind of consideration that the Starshot proposal raises, which is the question of whether sending probes to a possibly inhabited world is something we should be doing in the first place. If Proxima Centauri b has even a remote chance of hosting life, even microbial life, then sending an Earth-built probe there raises questions about contamination. We have on Earth very strict planetary protection protocols for the missions we send to Mars, designed to avoid contaminating any possible Martian biosphere with Earth microbes. The same kind of considerations would, in any future probe to a possibly habitable exoplanet, need to be carefully thought through. Whether the planet is currently habitable or not, the question of what we ethically owe to the possible biospheres of distant worlds is one that, in any serious interstellar exploration era, would have to be addressed. In the absence of probes, what we have are remote observations from Earth and from space. The next decade of those observations should, as we have discussed, settle the question of whether the planet currently has an atmosphere, what kind, and what its surface conditions are like. By the early 2030s, the picture should be, in its essential outlines, clear. Whether the planet has an atmosphere, what kind of atmosphere it has, if any, whether the atmospheric chemistry suggests any kind of disequilibrium that might be consistent with biological activity, whether the surface, beneath the atmosphere, has any features that might suggest oceans or other liquid bodies. The answers to these questions, while not as definitive as a direct sample return mission would provide, will be enough to settle the broad question of whether the planet is currently habitable. By 2050 or so, we should know with high confidence whether Proxima Centauri b currently hosts any chemistry consistent with biological activity. If the answer is yes, the implications are profound. If the answer is no, the implications are also significant, just in a different direction. Either way, the answer will arrive. The work of getting there is underway. Part 13, The Mournful Turn. There is a small philosophical aside worth indulging here before the final stretch of the story. The question of whether a planet is currently habitable is, in some ways, a different question from the question of whether the planet was ever habitable. The two are not the same. The simple version of the search for life beyond Earth, the version that gets the most popular attention, is the present tense question. Is there life out there now? The richer version of the question is the historical one. Was there ever life out there? The historical version has more possible answers. The planet might have life now. The planet might have had life once. The planet might never have had life at all. Three possibilities, two of which involve life having existed at some point. If we take the historical question seriously, then the universe of possibilities expands. Some fraction of the planets we are now studying, even if they are currently uninhabitable, may have hosted life in earlier eras. The atmospheric stripping that has rendered them currently uninhabitable may have happened after some period of habitability, not before. The fossil record of those long-dead biospheres, if it exists in any form that could be detected from far away, would be one of the more remarkable kinds of evidence we could ever find. We are not currently equipped to find it. The technology required is far beyond what we have. But the possibility, conceptually, exists. There is a particular kind of melancholy that comes with the picture of a planet that may once have been alive and is no longer. There is a particular human resonance to the picture of a once habitable world, because the picture is, in some sense, a longer-term version of what we are doing to our own atmosphere right now. Earth, on geological timescales, has had its atmospheric composition substantially altered many times. The early atmosphere was very different from the current one. The transition from the original atmosphere to the oxygen-rich one, around 2.5 billion years ago, was driven by the rise of photosynthetic bacteria and was, in its way, a planet-scale chemical revolution. Earth, in our own time, is going through another atmospheric transition driven by the burning of fossil fuels. The transition is, on geological timescales, fast. The conditions of human civilization, which have been comparatively stable for the past 10,000 years, are being altered on the timescale of a few centuries by the cumulative effect of human activity. The picture of Proxima Centauri b losing its atmosphere over billions of years is, in some respects, a slow-motion version of the kind of change Earth might also undergo on timescales we cannot quite see. The mechanisms are different, the timescales are different, but the underlying pattern of a planetary atmosphere being shaped by external forces over time, with consequences for the kind of life it can support, is structurally similar. Earth's situation is, by any reasonable estimate, much better than Proxima b's, but the same physical processes that are in operation on the distant world are, on a slower clock, in operation here as well. The melancholy is, in some sense, deeper than the melancholy of a planet that was never habitable in the first place. A planet that never had life is, in some sense, just a rock. A planet that had life and lost it is, in some sense, a place. A place where, perhaps, things happened, where chemistry mattered, where, for some span of time, the universe was experiencing itself in some local way before the conditions changed, and the experiencing stopped. There is something almost poetic about the geometry of the situation. The closest, possibly habitable world to Earth is, by every available measurement, in trouble. Not currently dead, by definitive measurement, but probably so. Not impossibly inhospitable, but very probably uninhabitable in any familiar sense. The closest, possibly habitable place is, on the best science we have, the closest, possibly dead place. The proximity that, in 2016, made the planet seem so promising has, in 2025, become the proximity that makes the planet's likely sterility most painfully visible. Most of the time, when we contemplate the question of life elsewhere, we imagine it as a binary. Either there is life out there, or there is not. The middle ground where life arose and then was lost is harder to imagine, because it is harder to access emotionally. But the middle ground, on the most recent science, is genuinely possible. Some fraction of habitable zone planets around active red dwarfs may once have hosted life and now do not. Proxima Centauri b is, by the current evidence, a candidate for being one of those. If this scenario is correct, then the universe contains, somewhere in the galaxy, a quietly large number of dead worlds. Not bare rocks that never had a chance. Worlds that had a chance, took it, ran with it for some span of time, and then lost. The timescales of stellar evolution, the realities of stellar wind and atmospheric stripping, would mean that, around active red dwarfs especially, this fate is not uncommon. The galaxy on this picture is not just full of uninhabited planets, it is also full of formerly inhabited planets. That is, when you sit with it, a different kind of cosmic loneliness than the simple version. The simple version says we may be alone. The richer version says we may be in the company of ghosts. Worlds that, at some point in cosmic history, hosted whatever the local equivalent of cells was, that did whatever the local equivalent of chemistry was, that achieved whatever the local equivalent of life was, before their stars or their atmospheres or their conditions ran out and the whole experiment ended. There is a particular thought that this version of cosmic loneliness invites, which is that loss in the universe at the cosmic scale is built into the structure of things. Stars are born, burn, age, and die. Their planets, in turn, go through phases that depend on the stars. Conditions for life, where they exist, are time-limited, not always for the reasons we are used to thinking about. Earth eventually will be uninhabitable too when the sun's main sequence, life, ends and the red giant phase begins. The end will come slowly, over hundreds of millions of years, but it will come. The pattern on the cosmic scale is one of conditions being temporary. The interesting things happen during the windows when the conditions are right. The windows close, the conditions change. The interesting things, if there were any, end. The universe in this picture does not contain permanent things. It contains slow processes that produce, briefly, the conditions for complexity, before those conditions change and the complexity ends. Proxima Centauri b on this telling is the closest of those possible ghosts, 4.24 light-years from our own home, around the closest star to our Sun, a planet that may have been once the closest thing to a fellow traveller in the local galaxy, and may now be the quietest of empty places. Part 14. Coming Home. We did not set out to find dead worlds. We set out to find planets at all in the early 1990s when the first exoplanets around Sun-like stars were just beginning to be detected. The question of habitability in those early years was largely theoretical. By the time real habitable zone planets started showing up in the catalogues in the 20-teens, the question shifted from theoretical to observational. By the time we had instruments capable of telling us anything specific about the conditions on those planets, in the 2020s the question shifted again, from is the planet in the habitable zone to is the planet actually habitable? Proxima Centauri b is, in this evolution of questions, a particularly informative case. The discovery in 2016 was framed in terms of the older question, habitable zone position, closest, possibly habitable world. The narrative was, briefly, optimistic. Subsequent observations, particularly the flaring measurements of Howard in 2018 and MacGregor in 2021, shifted the narrative. The newer observations did not change the orbital position of the planet. They changed our understanding of the environment the planet sits in. There is one more layer of caveat worth adding, which is that probably not currently habitable is doing a lot of work in any honest summary. The probability is not zero on any current model. There are scenarios particularly involving an unusually strong planetary magnetic field or an unusually thick atmosphere from the start, or a combination of both, in which Proxima Centauri b could have retained substantial atmosphere despite the stripping. Those scenarios are not the most likely on the current evidence, but they are not impossible. The honest position is one of probability rather than certainty. The probability has shifted over the past decade from probably yes to probably no, but it has not become certainty in either direction. The honest current position in the literature is that Proxima Centauri b is probably not currently habitable, despite its orbital position, because of cumulative atmospheric stripping by the host star's activity over billions of years. The probably is doing real work in that sentence. The case is not closed, but the trajectory of the evidence over the past decade has been steadily in this direction. Each new observation has tended to make the planet look less habitable than the previous picture suggested, not more. There is a thought worth holding on to before we close. The work of this kind of astronomy is, in some respects, more honest than the popular framing usually allows. The popular framing since the discovery of Proxima Centauri b in 2016 has been about the closest possibly habitable world. The frame is not wrong in any strict sense, but the frame, taken alone, hides the harder reality, which is that possibly habitable is doing a great deal of work in that phrase. The probability, of habitability on any specific candidate is one of the things the careful science is trying to estimate. For Proxima Centauri b, the estimate has been, over the years, declining, not because of any single dramatic finding, because of the accumulating weight of careful observations. That kind of slow downward revision is, in some sense, the opposite of the way the popular discourse usually works. Popular discourse loves dramatic upward revisions, where a quiet candidate is suddenly revealed to be more interesting than expected. Slow downward revisions, where a celebrated candidate is gradually shown to be less interesting than the headlines suggested, are less popular. They get less coverage. They are more difficult to fit into a satisfying narrative arc, but they are real. And they are, in the long run, more common than the dramatic upward revisions. Most exoplanet stories, when they are followed carefully over many years, end up being more nuanced than the original press cycle suggested. Proxima Centauri b is a particularly clear example of this pattern. The diamond planet is another. K2-18b is, in some respects, a third. The pattern is recurring. It is part of how the field actually works. That kind of self-correction where the field's collective view evolves over years as new data accumulates is one of the deepest strengths of the modern scientific method. It is not always pretty. It can produce confusion in the public-facing narrative, as different stages of the developing picture get reported as if they were the final answer. But over time, the corrections do their work. The picture sharpens. The early dramatic claims, when they are wrong, get walked back. The careful follow-up work, when it produces more accurate but less dramatic conclusions, eventually wins out in the literature. The discipline of the field, taken as a whole, is the discipline of being willing to revise your picture when the evidence requires it. Proxima Centauri b's story, like many before it, is a small case study in this larger pattern. The constellation Centaurus is in the southern sky in the southern hemisphere. The constellation Centaurus is, by the standards of the southern sky, dramatic. It contains some of the brightest stars in the southern hemisphere, including Alpha Centauri at first magnitude and Beta Centauri at half a magnitude. From dark southern skies, the constellation is easily visible to the naked eye and forms a recognizable pattern that has been catalogued by every civilization that watched the sky from far enough south. The constellation has been associated with the centaur Chiron in Greek mythology, the wise teacher of heroes, who, after being accidentally wounded by a poisoned arrow, gave up his immortality to free the Titan Prometheus. The Greeks placed Chiron in the heavens after his death, where he has been observed by every civilization that watched the sky over the southern horizon. The Babylonians had a different name for the same pattern of stars. The Egyptians had another. Almost every culture that watched the sky from the southern hemisphere built a story around this collection of stars, which contains, among others, the bright Alpha Centauri pair that is the gateway to our nearest stellar neighbours. From the northern hemisphere, particularly in latitudes north of about 40 degrees, the constellation never rises above the horizon. Proxima Centauri itself, even when it is above the horizon, is far too dim to see with the naked eye. To find it, you need a small telescope, careful coordinates, and very dark skies. Most people, even amateur astronomers, never see it. But the star is there. Around it, every 11 days, a small Earth-mass planet is making its lap of its sun in its 11-day orbit, with whatever atmosphere it currently has, with whatever surface conditions exist. The planet is too small and too close to its star to be directly imaged by current instruments, although that may change in the late 2020s. The planet is too distant for any probe we have yet built to reach. The planet for now exists for us only as a set of inferred parameters from radial velocity measurements and from theoretical models of how its atmosphere should have evolved. We thought, in 2016, that we had found the closest possibly habitable planet to Earth. We were not wrong, in the strict sense. The planet does sit in the habitable zone. But the realization since 2017 has been that habitable zone position is only the beginning of the question, not the end. The harder question of whether the conditions on the planet are actually compatible with life is one that the next decade of observations will answer, but that the current evidence already weights toward no. There is a thought I want to leave you with before sleep. The story of Proxima Centauri b is, in some sense, a story about how human expectations and physical reality can diverge. We expected in 2016 that the closest possibly habitable world would be a place we could one day go to. We expected that the planet, by its proximity, was special. We expected that the conditions on it were broadly similar to Earth's, just a smaller star away. Subsequent observations have revealed, slowly, that the expectations were wrong. Not because the planet is not there, not because the orbital position is not in the habitable zone, but because the conditions on the planet after billions of years of stellar bombardment are probably not what we hoped. The closest possibly habitable world is, in fact, the closest possibly dead world. The proximity, which once gave us hope, now gives us, more accurately, a clear view of how harsh red dwarf habitability really is. That kind of revision of expectations is, in some sense, the deepest service that careful science provides. It is not the dramatic discovery of new things. It is the slow, careful, often disappointing revision of our pictures of the universe to match the universe as it actually is. The universe, after all this, has not turned out to be quite what we hoped. The closest, possibly habitable world is probably dead. The diamond planet is probably not made of diamond. K2-18b's atmospheric biosignature is probably not yet definitive. The early dramatic claims have, in case after case, been gradually refined into more accurate but less dramatic pictures. That is, in the long run, what science does. It improves the accuracy of the picture, even when the improvements make the picture less satisfying. The work is honest. The work is slow. The work is necessary. The picture, after all the revisions, is closer to the truth than it would be without the work. That is enough. You can let the planet go for tonight. The work of finding out what is really there is being done slowly, by people you will never meet. The flaring measurements continue. The atmospheric stripping models are refined. The next generation of instruments is being built. There is one more thing I want to leave you with, before sleep, about the timing of all of this. The MacGregor flare we have been talking about happened on the 1st of May, 2019. The light from that flare, leaving Proxima Centauri at the speed of light, took 4.24 years to reach Earth. The data we now have about the flare came back in those photons. The photons that left Proxima during the flare arrived at Earth in late 2023, where they were collected by instruments and analysed by the MacGregor team, with the analysis published in 2021 based on partial data and refined in subsequent years. The flare itself, on the planet, would have been an instantaneous event. The 7 seconds of extreme radiation reached Proxima Centauri b within tens of seconds, given the planet's orbital distance. Whatever atmospheric damage was done by the flare was done quickly, on the planet in 2019. We are watching in 2025 the after effects of an event that, on the planet, happened more than half a decade ago. The light is delayed. The information is delayed. The picture we are building of the planet's current state is, by these delays, always slightly out of date. That is, in some sense, the deeper philosophical fact about all of this kind of work. Astronomy is, fundamentally, the study of the past. Everything we observe has happened by the time we observe it. The closest star to our Sun is, by the time its light reaches us, 4 years in the past. The most distant galaxies we can see are billions of years in the past. Modern cosmology is, in some real sense, archaeology of light. We dig up information from the past by looking at where it has accumulated. The further away we look, the deeper in time we look. Proxima Centauri at 4 light-years is recent past. The Andromeda Galaxy at 2.5 million light-years is much deeper past. The most distant galaxies we can see with the help of telescopes like JWST are billions of years in the past. We are always, when we look at the cosmos, looking at history. The past, in this kind of work, is the only present we ever have access to. There is, in some sense, a meta-point worth making about the work itself. The slow, patient accumulation of evidence about a single distant world by hundreds of researchers across decades is one of the more remarkable forms of human cooperation we have. Nobody is in charge. No central authority dictates which observations get done. The work proceeds by individual choice, by team formation, by funding decisions in many different countries, by peer review and follow-up and reanalysis. The picture, when it emerges, is the product of all of these decentralized activities, none of which alone would produce the picture we now have. That kind of large-scale cooperation on a question that does not have any practical implications for human civilization in any near-term sense is unusual in human history. We do occasionally do work like this, the mapping of human languages over centuries, the building of the world's libraries, the slow accumulation of mathematical knowledge across cultures, but these examples are exceptions rather than the rule. Most human work, on most questions, is much more localized, much more goal-directed, much more clearly motivated by short-term outcomes. Exoplanet astronomy, particularly the careful characterization of specific planets like Proxima Centauri b, is one of the more durable examples of long-term cooperative inquiry. The question takes decades. The cooperation, by necessity, also takes decades. The patience is, in some sense, the work. By the time the answer is in, most of us listening tonight will not be alive to read it. But the answer will be in eventually. The patience of the work guarantees that. The instruments are being built, the funding is being allocated, the teams are being trained. The slow, steady work of finding out on the time scale of generations will not stop. Good night. Sleep well. The closest star to our Sun is still doing its slow, patient work, 4.24 light-years away. Its planet, if it is still there in any meaningful sense, is still in its 11-day orbit. Whatever atmosphere it has is doing whatever thin atmosphere does on a tidally locked planet around a flaring red dwarf. The flares continue. The bombardment continues. The slow stripping continues. The story is exactly tonight at the place where we left it. The slow stripping continues. The flares continue. The faint signal of whatever the planet currently is, encoded in the photons that left Proxima 4 years ago, continues to arrive on Earth, where instruments collect it and analysts process it, and the picture, very gradually, gets a little sharper. The light continues to arrive. We continue to learn. The picture, one observation at a time, gets a little sharper, even as it gets, in some respects, a little sadder. There is, far across most of 4 light years of empty space, a small dim red star making its slow, patient burn. The star is small, the star is dim. The star, by every measurement we have made of it over the past century, is unremarkable in almost every respect, except its proximity. Its proximity is the only thing about it that matters for our story tonight. Around that star, every 11 days, a planet that may once have been more than what it is now is making its lap. Whatever it currently is, the star continues to flare, the wind continues to blow, the slow, patient stripping of whatever atmosphere remains continues to proceed on its own clock. None of this depends on whether anybody on Earth is watching tonight. None of this depends on whether anybody on Earth in any future generation ever finds out the answer. The work of the universe goes on, regardless of the audience. The light from Proxima Centauri reaches Earth tonight after 4.24 years of travel through empty space. Whatever the planet is right now, we will not see what it is right now until 2030. The lag is built into the geometry of everything. We see, always, the past. Good night. Again, sleep gently. The planet is still there, possibly. The light is still arriving. The work continues. The story, on the timescales of the stars, is still being written. There is one final thought I want to leave you with before sleep. We have spent this evening with a story that is, in many of its details, quietly mournful. A planet that may once have been a place. A possible biosphere lost to billions of years of stellar bombardment. The closest, possibly habitable world, probably no longer habitable. The universe on this telling is a place where conditions for life arise and then are lost. But the same universe on the same kinds of time scales is also a place where conditions for life arise. The processes that produced Proxima Centauri B's possible early habitability are the same processes that produced Earth's habitability. The fact that Earth's window is still open, while Proxima B's may be closed, is, in some sense, a matter of stellar luck. The Sun is quieter than Proxima. Earth's atmosphere has been less stripped. Earth's life, where Proxima B's may have been lost, has had the chance to continue. That contrast is, in some sense, the deeper meaning of the comparison. Not that the universe is full of dead worlds, but that the universe is full of worlds whose conditions vary, whose biospheres come and go, whose stories are still being written, even when, on any particular evening, one of those stories has reached its quiet end. Proxima Centauri b on this picture is one chapter in a much longer book. The book is still being written. We are, all of us, alive in the middle chapters. Sleep well. The closest star to our Sun is doing its slow, patient burn 4.24 light years away.